Artemis I will be the first integrated flight test of NASA's deep space exploration systems. The Orion spacecraft, the Space Launch System (SLS) rocket, and the supporting ground systems at NASA's Kennedy Space Center in Florida. After so many decades of shelved projects, of destroyed dreams of exploration, the way is once again paved for the Moon and then for the beginning of human exploration on other planets, starting with Mars. The high-speed lunar velocity re-entry is the top mission priority and a necessary test of Orion's heat shield performance as it enters Earth's atmosphere. Heating to nearly 2,760 degrees Celsius before splashing down in the Pacific Ocean for retrieval and post-flight engineering assessment. SLS is designed for deep space missions and will send the Orion spacecraft and cargo to the Moon, which is nearly 1,000 times farther than where the International Space Station resides in low Earth orbit. The rocket will provide the power to help Orion reach a speed of nearly 36,400 km per hour, the speed needed to send it to the Moon. A central core stage housing propellant tanks, engines, avionics, and attach points for a pair of solid rocket boosters. 4 liquid propellant RS-25 engines powered by cryogenic, or supercooled, liquid hydrogen and cryogenic liquid oxygen from the core stage. 2 solid fuel, side-mounted booster motors that provide the majority of thrust and steering for the rocket during the first 2 minutes of flight, after which they are jettisoned. An upper stage fueled by liquid hydrogen and liquid oxygen for in-space propulsion after separation from the core stage. And capabilities. SLS has the largest payload mass and volume of any existing rocket and is the only rocket that can safely send Orion, astronauts, and cargo to the Moon on a single mission. More mass and volume translate into fewer launches of fewer pieces, requiring less assembly time in space and less overall risk. We therefore return to the path traced by the Apollo program, by Wernher von Braun and his exceptional team. Such sensational results as to still find some denigrators, despite all the incontrovertible evidence. SLS benefits from over 50 years of NASA experience with liquid oxygen and liquid hydrogen propellants, along with advances in technology and manufacturing practices. SLS development and manufacturing operations take advantage of resources established for the Space Shuttle, including the workforce, manufacturing processes, tooling and facilities, transportation logistics, launch infrastructure, and liquid oxygen and liquid hydrogen propellants. SLS evolvability supports robust human exploration beyond low Earth orbit as exploration missions become more complex and demanding. Future missions and configurations. To fulfill America's future needs for deep space missions, SLS will evolve into increasingly more powerful configurations. Each succeeding SLS block variant grows more capable through upgrades to the engines, boosters, and upper stage, providing a flexible platform for a variety of human and robotic deep space missions, rather than requiring the development of entirely new rockets to increase performance. SLS uses common design elements that can interface with the ground systems at Kennedy, the Orion spacecraft, and future payloads, reducing the complexity of deep space missions over time. In addition to flying Orion, SLS can also be outfitted with wide-diameter payload fairings in varying lengths for cargo and robotic science missions. The Artemis I mission will use the first configuration of the SLS rocket, known as Block 1, capable of lifting more than 27 tons to orbits beyond the Moon. more than 38 tons to deep space, including Orion and its crew. The Block 1B variant incorporates several upgrades to improve SLS performance, allowing the rocket to launch larger and heavier payloads to deep space destinations. SLS Block 1B uses the same core stage and twin 5-segment solid rocket boosters as the Block 1 rocket. New production RS-25 engines will provide slightly more thrust than the Shuttle-era engines and cost 30% less to manufacture. Most of the increase in performance for the Block 1B rocket will come from replacing the single-engine ICPS with a more powerful 4-engine exploration upper stage and a universal stage adapter to CA. RRY Orion, along with large cargoes for exploration systems needed to support a long-term presence at the Moon. The SLS core stage is the most powerful rocket stage NASA has ever built. The SLS measures approximately 65 meters tall and 8.5 meters in diameter, excluding thermal protection system foam and flanges. The stage fully fueled weight, excluding engines, is 1,090,000 kilograms. It was manufactured by the lead contractor for the core stage, Boeing, at NASA's Michoud Assembly Facility in New Orleans using state-of-the-art manufacturing equipment. The SLS core stage is designed to operate for the roughly 8-minute Artemis I launch from ground and ascent to Earth orbit, reaching speeds of faster than 28,160 km per hour, or nearly 23 times the speed of sound, Mach 23, and more than 161,500 meters in altitude before it separates from the ICPS, Orion stage adapter, and Orion. The core stage was a major new development effort for the SLS program, while other key elements, such as the RS-25 engines, solid rocket booster structures, and ICPS